Welcome to the deep dive. Today, we're plunging into a field that, well, it's often invisible, but it fundamentally underpins nearly every facet of our modern existence.
It really does.
Think about it. The water we drink, the cars we drive, sophisticated medical equipment, global supply chains all rely on these intricate control systems.
They're absolutely everywhere, constantly regulating, optimizing, keeping things running smoothly.
Exactly. But have you ever stopped to really consider how this pervasive fundamental discipline evolved? What were the philosophical battles that shaped its very nature? How did we get from ancient ingenuity to the complex intelligent systems we interact with today?
It's a fascinating story, full of twists and turns.
So we're embarking on a deep dive into Professor Ali Khaki-Sedigh's really profound work, Control Systems, a historical and philosophical perspective.
A fantastic resource.
And this isn't just about the what of control systems. We want to get into the why and the how. We're exploring that intricate interplay between history, philosophy, and engineering that really defines this critical field.
That intersection is key.
Now, for those of you listening, we know you're deeply immersed in interdisciplinary systems, science, engineering, philosophy, history, control systems, AI, energy, futurism.
Right, this is aimed at a high level of expertise.
So prepare for a nuanced discussion. We'll delve into intricacies often overlooked. Our journey starts way back with ancient ingenuity. Then we'll trace the emergence of mathematical formalism.
The move towards rigor.
Exactly. Then unpack the triumphs and maybe the unexpected limitations of modern control theory. Then pivot to cutting-edge postmodern paradigms. And finally, peer into the future. Consider the ethical implications too.
Which are becoming increasingly important.
Okay, let's unravel this. To truly appreciate the sophistication of modern control, we have to look back, way back actually, to the earliest sparks of human ingenuity.
Before any formal principles existed.
Right. We're talking automatic control mechanisms that show this kind of inherent drive for self-regulation, even in ancient times.
Like Sisyphus' water clocks.
Exactly. 1st century AD, ancient Greece. These weren't just simple dripping vessels. Sisyphus introduced constant-level reservoirs using a float-regulated valve system.
Which is a remarkably early form of feedback, right?
Precisely. Designed to maintain a consistent flow rate and, crucially, improve timekeeping accuracy. The whole concept of an escapement controlling energy release in a regulated way was already there.
It's fascinating how these early ideas laid the groundwork. And then you have Heron of Alexandria, also 1st century AD. His works, like the Pneumatica and the Automaton Theater, are just astounding mechanics.
Those automatic temple doors.
Yes. Activated by fire, a really sophisticated early control system. Fire heats air, forces water into a bucket, its weight increases, turns door spindles via ropes and pulleys, raises a counterweight.
A complete cycle. Command input, process, feedback.
Absolutely. But what I find particularly intriguing is that the mechanism was deliberately hidden, concealed to create mystery, enhance the perceived power of the gods.
That's a really interesting parallel.
Doesn't it resonate with our modern debates about black box AI, transparency and control systems? It suggests these questions of trust and understanding aren't new at all. They're embedded deep in the history.
That's a profound connection. And beyond religious contexts, there were practical examples too, like the Chinese south-pointing chariot.
Ah, yes, indicating south, regardless of orientation, an ancestor to modern navigation in a way. Early directional control.
And then the Islamic Golden Age, roughly 800 to 1200 AD. Just an incredible acceleration in science and technology.
A real flourishing. Scholars like the Banu Musa brothers, their Kitab al-Hayal, or Book of Ingenious Devices. Over 100 mechanisms detailed.
And not just quantity, but pioneering concepts.
Exactly. Hydrostatics, aerostatics, automatic valves, delayed action systems, and crucially, their texts show the first historical use of crankshafts. Think about how fundamental that is.
Absolutely fundamental.
And, even more relevant for us, the pioneering use of on-off control with upper and lower limits.
A system still widely used today.
In countless applications, yes. It's not just a historical footnote. It's a direct lineage.
And then Al-Jazari, 1206 AD, his Book of Knowledge of Ingenious Mechanical Devices, he really synthesized and advanced these techniques, didn't he?
He did. And his book wasn't theoretical. It was intensely practical.
Ugh.
Detailed descriptions focused on construction, clear impact on later developments, even things like steam engines. It's hard to overstate his significance. Until modern times, there wasn't really another document from any culture offering such rich instructions for machine design and assembly.
Now, for us, as researchers steeped in the latest system science, it's tempting to look at these ancient mechanisms and think, okay, quaint, but maybe not directly relevant to my work on, say, adaptive neurofuzzy control.
It's a fair question.
So why is revisiting this history, this philosophical lineage, so critical? What does it really offer us when we're tackling today's complex problems?
That gets to the heart of engineering knowledge, doesn't it? While these specific ancient solutions might not solve modern problems directly, looking back gives us invaluable insight. It shows the necessity of a holistic perspective.
Seeing the bigger picture.
Right, and understanding the inherent challenges engineers have always faced. When you examine the critical views of theories throughout history, you see engineering isn't just this smooth, linear progression of successes.
It's messy, full of debates and shifts.
Exactly. It helps us understand why paradigm shifts happen, connecting historical debates with the philosophical aspects of design that have always been intertwined. It allows us, as engineers, to see ourselves in a grand tradition of learning, one that includes both amazing success and, frankly, illuminating failure.
So it fosters a deeper engagement beyond just the technical nuts and bolts.
Precisely. History helps us move from just focusing on narrow, complicated technical fixes towards a more comprehensive problem-solving approach. It might not predict the future perfectly, but it illuminates the conditions and influences that shape how technology evolves, pushing us towards a broader, more critical view.
That's a compelling case for broadening our perspective, which leads nicely into this. Why is philosophy often seen as, well, abstract, so crucial for engineers?
Yeah.
People sometimes call engineers the unacknowledged philosophers of the postmodern world.
I think philosophy helps us define and comprehend the very mission of engineering itself. Using philosophical principles helps clarify our goals and methods.
Beyond just the technical methods.
Yes, exactly. It gives us a framework for tackling professional problems that pure engineering methods can't solve alone. Think about ethics, social responsibility, environmental impact, safety, risk, the values embedded in our designs. These are philosophical questions at their core.
Which are becoming unavoidable in areas like AI and autonomous systems.
Absolutely. And for engineering education, integrating philosophy is vital for promoting critical thinking, especially for the complex, multi-dimensional problems you encounter in system science. It also encourages self-reflection, examining our own understanding, our practices, our designs, and their impact.
That's a crucial point, recognizing engineering's broader impact. Which brings us to a key distinction: engineering epistemology. How does engineering know things? How does its way of generating knowledge differ fundamentally from science?
There are several key differences, really important for our audience to appreciate. First, let's call it phenomenological sufficiency. Scientists, generally, aim for theories with deep ontological correspondence. They want to explain why things happen.
Getting to the fundamental truth.
Right. Engineers, however, might be perfectly satisfied with theories that primarily predict phenomena well enough to allow effective control, even without a full why explanation. Think about a PID controller.
A classic example.
It works, it controls the process, maybe using simplified models or lookup tables based on empirical data. It's sufficient because it has predictive and control utility, even if the underlying physics isn't modeled down to the last detail.
Okay, so predictive power over deep explanation sometimes. What else?
Second, engineering considers a wide variety of target qualities. Science often focuses on physical phenomena, but engineering has to incorporate socio-technical qualities, cost, time to market, safety, usability, maintainability. These are critical design constraints, but often outside traditional scientific scope.
Things science might abstract away.
Often, yes. Third, instrumental properties are paramount for engineering theories. They must be practical, efficient, usable within resource limits. Scientific theories can afford complexity for deeper analysis, but engineering theories need to be workable tools.
And
Finally, engineering often employs multiple overlapping theories. Scientists usually seek a single, broad, precise theory. Engineers, pragmatically, might use several unfalsified theories, simultaneously rules of thumb, alongside precise algorithms, maybe. Each has its place, its level of precision, its applicability. You trade off based on practical needs. A simple heuristic might still be valuable even if a complex algorithm exists.
it really highlights that engineering isn't just applied science. It's a distinct way of knowing with different goals and methods. And this is really clear when engineering discoveries actually precede the scientific explanation, isn't it?
Absolutely. That happens more often than you might think. Proportional control, for instance, was used in various applications long before a comprehensive scientific theory of feedback really explained it formally.
And tuning methods.
The Ziegler-Nichols method for PID controllers is a perfect example. Developed empirically in industry in the 1940s, became a standard. The deep scientific grounding came later.
Even advanced techniques.
Even model predictive control, MPC. Highly sophisticated, uses predictive models. But it was developed and used in process industries before it was thoroughly studied and understood from a purely scientific, theoretical standpoint. It really underscores that pragmatic, problem-solving core of engineering.
That sets the stage perfectly for discussing the emergence of mathematical principles. But before we dive into that formalization, maybe we should briefly categorize the kinds of systems control engineers actually deal with. We know the boundaries are fuzzy, especially for this audience, but what's the crucial distinction beyond just inputs-outputs that really changes the game? Where does something like emergence come in?
That's the critical point, emergence. Okay, so roughly we can think of 4 types, knowing it's a spectrum. First, simple systems, usually single input, single output, SSO. Their internal dynamics are linear or can be linearized pretty well.
Like a basic DC motor speed control or a tank level control.
Exactly. Then you have complicated systems. These are often multi-input, multi-output MIMO with significant interactions between subsystems. Maybe some bounded uncertainty, but crucially, no emergence.
So like a distillation column in a chemical plant or maybe aircraft control surfaces working together, you can model them even if it's complex.
Right, you can generally model their behavior quite extensively, even with interactions.
Sure.
The real shift happens with complex systems. These are inherently uncertain, strong interactions, and crucially, these interactions can lead to emergence. Even CISO systems can be complex.
Give us an example.
Think of an ant colony. Individual ants follow simple rules, right? But the colony as a whole exhibits incredibly complex adaptive behaviors, foraging patterns, nest building that aren't explicitly programmed into any single ant. That's emergence.
Or neural networks.
Perfect example. The collective behavior of simple interconnected neurons leads to emergent properties like learning and pattern recognition. Or traffic flow individual drivers following simple rules can lead to complex, unpredictable emergent phenomena like phantom traffic jams.
And the final category.
Complex adaptive systems, or CAS. These are even more intricate. They're complex systems with time-varying characteristics, capable of self-organization and adaptation. They can fundamentally change their own structure and behavior over time, leading to novel, unexpected outcomes you couldn't have predicted from the initial design.
So systems that learn and evolve on their own.
In essence, yes. Think about ecosystems, immune systems, or maybe even some advanced multi-agent robotic systems or evolving economic markets.
Okay, with that appreciation for system complexity, you can really see why mathematics entering the picture was such a revolution. It wasn't just adding precision, it enabled tackling these harder problems.
It truly was transformative. This mathematical foundation started solidifying with fields like the calculus of variations, which is all about optimization. Johann Bernoulli's brachistochrone problem back in 1697, finding the path of fastest descent, is often cited as the birth of optimal control.
And then Euler, Lagrange, Legendre.
Right. The Euler-Lagrange equation for stationarity, Legendre's work on ensuring minimization, and later Weierstrass providing rigorous mathematical foundations in the 19th century. These form the bedrock for modern optimal control theory.
And the concept of stability itself had to evolve mathematically, too, from just meaning standing firm to a precise mechanical definition. But early empirical methods struggled to guarantee it.
Exactly. They lacked a systematic framework. You could say mathematics formally entered control theory with James Clerk Maxwell's paper on governors in 1868.
Which Wiener called the first significant paper on feedback mechanisms, Maxwell as the father of control theory.
He really laid the groundwork, and a major driving force for stability studies in the late 19th century was the huge problem of steam engine governors oscillating wildly.
Instability costing economies.
Absolutely. Hundreds of thousands of engines in Russia and Western Europe weren't regulating speed properly. Scientists like Chebyshev in Russia, Maxwell and Ruth in Britain, they tackled this by modeling governors and deriving stability conditions. But their work, though groundbreaking, remained somewhat isolated initially.
Engineers found the math too abstract or the assumptions unrealistic for their immediate problems.
That was often the case, yes. The impact on industry was limited at first.
But then came Lyapunov, Alexander Mikhailovich Lyapunov. His work, initially obscure in the West, would prove absolutely foundational.
Monumental is the right word. His 1892 doctoral thesis, The General Problem of the Stability of Motion. It's incredibly rare for a PhD thesis to have such a profound, long-lasting impact. especially after being relatively unknown outside Russia for decades.
What made his approach, his second method, so revolutionary?
Its elegance and power. It provided a way to guarantee system stability without explicitly solving the often incredibly complex differential equations describing the system. Essentially, if you could find a specific type of function, what we now call a Lyapunov function, sort of like a generalized energy function, and showed that this function always decreases over time along the system's trajectories, then you knew the system was stable.
A profound abstract leap. No need to solve the dynamics directly.
Exactly. It was a huge theoretical advance. Interestingly, Lyapunov was heavily influenced by astronomical stability problems, where ensuring orbits remained bounded. Lyapunov's stability was often more critical than ensuring they converged to a single point, which is asymptotic stability.
It's still amazing that such a fundamental theory stayed isolated for so long. What finally brought it to the West? What broke down that communication barrier?
It really happened in the late 1950s and early 1960s. The main catalyst was the space race.
Sputnik.
Sputnik 1 was a major wake-up call. The complex control problems of rocketry and satellites demanded new theoretical tools. Key events helped too. The first IFAC World Congress in Moscow in 1960 was huge.
A major meeting of minds.
Definitely. Plus, a pivotal article by R.E. Kalman and J.E. Bertram came out that same month. And you had figures like Solomon Lefschetz, Kalman, Lassalle, actively seeking out and disseminating Russian mathematical work. English translations of Russian journals started appearing too.
So a combination of geopolitical pressure and dedicated academic bridge building.
Precisely. A classic example of how global events and collaboration can accelerate scientific progress.
Okay, that brings us right to the cusp of modern control theory. But before the full flowering of state-space methods, there were crucial transitions in the classical era, especially driven by telecommunications. Harold Stephen Black's negative feedback amplifier in 1927. That was huge, wasn't it?
Absolutely pivotal. He was tackling the problem of distortion in telephone repeaters. High gain meant more distortion, noise.
A major limitation.
Black's brilliant, almost counterintuitive idea was to feed a portion of the output signal back into the input out of phase. This dramatically reduced distortion while still maintaining useful amplification.
And it was kept secret for a while.
Until 1934, yes. Strategic importance. He got crucial help from Harry Nyquist. Nyquist's 1932 paper, Regeneration Theory, laid the groundwork for Nyquist analysis.
A cornerstone of classical control.
Definitely, a powerful graphical tool for analyzing stability without solving differential equations. Black himself called the instability singing. Nyquist introduced the concept of conditional stability, the tricky idea that a system could become unstable even if you decrease the loop gain. Not intuitive at all.
And then Hendrik Wade Bode enters the picture. Gain and phase margins, the critical point in Nanish-1
Bode plots. His frequency response analysis, those straight line approximations, fundamental tools still taught today. And the concept of gain bandwidth limitation, a fundamental trade-off.
On the time domain side, MIT was active too.
Yes, Hazen and Brown were pioneers using mechanical differential analyzers to actually simulate control systems, cutting-edge stuff for the time. By the early 1950s, these classical techniques, a time response via ODEs, frequency response via Nyquist, Bode, transfer functions became the standard toolkit.
A kind of universal language for engineers across different fields.
That's a good way to put it. And industry was adopting things too, like Morris Leed's pneumatic PI controller patented back in 1920. And PID tuning rules, especially Ziegler-Nichols in the 40s, provided systematic procedures for practical implementation. Again, practice often leading theory.
It's that recurring theme again, warfare accelerating progress. World War II was an incredible catalyst for control systems. What were the specific military problems driving innovation?
Immense challenges. Guided missiles and torpedoes needed precise control for accuracy. Military aircraft needed much better stability, maneuverability, targeting systems.
Anti-aircraft guns.
Huge driver. Radar-guided tracking and targeting systems relied heavily on automatic control to hit fast-moving planes. Artillery fire control also advanced significantly faster targeting, higher accuracy. Think of gun directors, sometimes with a human integrated, predicting future positions, setting fuses in real time.
And the NDRC, the National Defense Research Committee in the U.S., coordinated a lot of this.
Yes, established in 1940, involving top scientists like Vannevar Bush, they directed research towards these critical military needs.
And this is where Norbert Wiener comes in, again, more formally, with his prediction problem for anti-aircraft fire.
Right. The NDRC tasked both Bell Labs and Wiener at MIT with predicting aircraft movements. Wiener proposed this groundbreaking mathematical approach using generalized harmonic analysis essentially, trying to statistically predict the unpredictable evasive maneuvers.
But there were limitations.
Significant ones. As researchers like Jan Willems later pointed out, Wiener's stochastic filtering struggled with deliberate tactical evasion. An enemy pilot isn't moving randomly. They're following tactical logic.
The math didn't fully capture the intent.
Exactly. The mismatch between the idealized mathematical model and the complex reality of combat meant Wiener's approach, while influential theoretically, only had a slight operational advantage during the war. Wiener himself was apparently uncomfortable with this widespread use of probability as a panacea for uncertainty, recognizing it overlooked goal-directed behavior.
Yet, despite those specific limitations, his wartime work directly sparked the birth of cybernetics. That really changed how he thought about control, didn't it?
Absolutely. His experiences, combined with his fascination with biology, led to his seminal 1948 book, Cybernetics. It started portraying machines that could adapt, learn, seem almost lifelike. It explored feedback, machine control, and crucially, the role of the human operator within the system. It transformed thinking about information and complex dynamic interactions.
And it influenced others.
Profoundly. Claude Shannon, with his mathematical theory of communication in 48, merged machine control and information theory. J. Wright Forrester, known for system dynamics, worked on servo mechanisms for aircraft. It created this vibrant, cross-disciplinary intellectual movement.
This era really culminated in the formalization of mathematical system theory, MST, particularly with the state space approach. This promised a unified, rigorous framework.
Kalman was central here, Rudolf Kalman. He really drove the emergence of MST as a scientific discipline, unifying disparate contributions into a cohesive, abstract mathematical framework. He strongly believed in focusing on the essential mathematics.
And the state space approach itself, what did it offer?
Introduced in the 1960s, it was much more detailed and mathematically rigorous than classical input-output methods. It provided deep theoretical insight, a common language. Critically, it allowed engineers to study the internal workings of dynamic systems, not just their external responses.
You can inside the box.
Precisely. It naturally handled multivariable systems, which classical methods struggled with, and it opened the door to sophisticated estimation, prediction, optimization techniques, the Kalman filter being the prime example.
Famously used in the Apollo program.
With incredible success, yes. A major triumph for MST.
But despite these huge intellectual leaps and successes like Apollo, MST had this famous Achilles heel. What were its inherent limitations? What was this theory-practice gap that started to emerge?
Well, the limitations stemmed partly from its philosophical underpinnings. Its reliance on reductionism, breaking complex systems down, often clashed with the holistic nature of real-world problems. Its deterministic assumptions bumped up against the pervasive indeterminism and uncertainty of reality.
The models were too clean.
Often, yes. The reliance on pure mathematical reasoning raised questions about the validity of knowledge derived from these idealized models. They often ignored aspects deemed irrelevant, leading to significant discrepancies with actual system behavior, mainly due to unmodeled dynamics. Simple cause and effect reasoning also becomes very difficult in highly coupled feedback systems.
And transparency issues?
Yes, confounding variables in the real world, plus issues understanding and controlling the behavior of increasingly complex systems. Perhaps the most profound issue was realizing that properties derived from the mathematical representation, like controllability or observability from state space matrices, didn't necessarily reflect inherent properties of the actual physical system. The matrices are a representation we choose, not reality itself.
This raises that fundamental question. What happens when elegant theories meet messy reality?
That's exactly where the Achilles heel showed itself. By the early 1970s, there was a real sense of crisis in the control community. People were reporting unexpected issues, even failures, when implementing MST in industry.
Why? What were the root causes?
Consistently, it came back to model simplifications and unaddressed uncertainty. Fuller had pointed out deficiencies back in '63, assuming LTI plants when reality is time-varying, neglecting noise, using lumped models for distributed systems. Rosenbrock in '71 critiqued optimal control as often infeasible, pointing out flaws like needing unknown noise statistics for Kalman filters.
And Horowitz.
Isaac Horowitz in '93 was even more forceful, highlighting the impracticability of much of modern control theory. He argued compellingly that feedback is fundamentally about dealing with uncertainty, directly challenging MST's deterministic core. The theory-practice gap persisted because expertise required deep, abstract math, but education often used oversimplified examples, creating a disconnect with complex industrial reality.
So how did the control community respond to this Achilles heel, this growing gap? It sounds like the over-reliance on idealized models meant a holistic view got lost, leading to entirely new schools of thought specifically designed to tackle uncertainty head-on, like adaptation, robustness, intelligence.
Precisely. The field had to acknowledge that uncertainty wasn't just noise to be filtered out, it was fundamental. This led directly to robust control.
Moving beyond just designing for small sensitivities to tackling inherent uncertainty more fundamentally, what was the core shift there?
It was a major conceptual leap. Instead of just small variations, robust control aimed for intricate mathematical frameworks that could guarantee performance and stability despite large, poorly characterized uncertainties. The term emerged in the 70s, Safanov, Davison, Pearson, Stats.
Building on earlier ideas.
Yes, the small gain principle from 63 was an early step. But a key moment came when studies showed that optimal controllers, like LQG regulators, were not inherently robust. That was a shock.
Optimality didn't guarantee robustness.
No, which led to a profound philosophical shift. Sometimes you could enhance robustness by relaxing the requirement for optimality. Trade off optimality for guaranteed performance under uncertainty. Many practical failures were traced to simply not being able to estimate model uncertainties accurately enough. Some researchers even started questioning the basic premise that you must assume something to know something to achieve control.
A radical rethink. Trading optimality for robustness. Now, what about adaptive control? Another way to handle uncertainty, but rooted more in biological ideas. What was its path?
Its origins are indeed in biology, organisms adapting to changing environments. In control, it means systems that monitor their own performance and adjust their parameters online to improve closed-loop behavior.
Sounds promising. How did it develop?
Well, the 50s and 60s were kind of an enthusiasm to disappointment era, high hopes, but limitations in hardware and theory led to failures. The X-15 adaptive flight control system crash in 67 was a major setback.
What turned it around?
Lyapunov theory, again, applying it to model reference adaptive control, MRAC, particularly by Parkes in 1966, provided crucial stability guarantees. That was the breakthrough needed for developing sound theories of adaptive control in the 70s. Then microprocessors made practical implementation feasible.
But there were still challenges.
Oh yes. The wake-up call came in the early 80s with Wars' counterexample. It showed that even mathematically stable adaptive controllers could behave badly, become non-robust when faced with unmodeled dynamics.
So stability wasn't enough.
Right. This sparked intense research into robust adaptive control, trying to guarantee good behavior like bounded signals, even with uncertainty. Philosophically, adaptive control focuses on dynamic adjustment, flexibility, real-time learning. Robust control focuses on predefined uncertainty bounds, guaranteeing stability across those conditions. Now there's a lot more synergy combining both approaches.
Okay, now for what feels like the most contemporary evolution, bridging AI and automatic control, intelligent control.
Yes. The term was introduced by Kei Fu back in 1971. He was looking at systems incorporating advanced decision-making, problem-solving inspired by human intelligence, a clear overlap between control and the emerging field of AI.
Examples.
Thinking about human operators as sophisticated controllers, autonomous robots, complex man-machine systems. Neural networks became a major component here.
Going back to McCulloch-Pitts in 43.
That was a key milestone, yes. Then Hebb's learning rule and 49 pathways strengthening with use. Woodrow and Hoff's Adeline and Madeline. Madeline was actually the first neural net applied to a real-world problem, echo cancellation on phone lines.
And Rosenblatt's perceptron.
Yes, 1957-58. Early single-layer network. His convergence theorem for linearly separable data was important. It all laid the groundwork for multi-layer perceptrons and eventually deep learning.
Alongside neural nets, we saw the rise of fuzzy logic and fuzzy control. This seemed to directly challenge classical mathematical rigor, didn't it?
It absolutely did. It came from doubts about whether classical math could handle the imprecise, vague concepts inherent in human language and reasoning, which are often crucial for controlling real-world systems. Lotfizadeh's fuzzy set concept in 1965 provided a way to represent these linguistic terms systematically.
But it faced resistance, major resistance.
Intense skepticism. Kalman, being a giant of classical control, was famously critical. Severe, ferocious, even brutal criticism, calling it wishful thinking, lacking basic concepts, having no chance of solving fundamental problems, leading to socially appealing slogans without the rigor of disciplined scientific work. He strongly opposed it as science.
Wow. Given that level of critique from someone like Kalman, how did fuzzy logic gain traction? What was its winning card?
The winning card was pragmatism. Engineers realize that demanding mathematical precision often makes real-world problems intractable or impossible to solve within practical constraints. Precision has a cost. Fuzzy logic offered a way to directly encode human expertise, heuristic rules, linguistic knowledge into a controller, even when a precise mathematical model was missing or too complex.
Bridging the gap using human-like reasoning.
Exactly. The first real practical demo was Mamdani in 1975, controlling a model steam engine with fuzzy logic. It showed it worked well for systems hard to model precisely. Since then, it's exploded in consumer products, washing machines, air conditioners, plus automotive, robotics, process control. Its practical utility won out over the initial theoretical objections.
So this whole evolution implies that feedback control, whether natural or engineered, fundamentally relies on models. But what kind of models, given this history? Primitive control was heuristic, artistic. Modern control became modeling, analysis, design.
Right. We traditionally relied on analytical mathematical modeling, deriving models from physical principles using state space, transfer functions, ODEs. Great for understanding, simulation, prediction, optimization, model-based design.
But for complex systems.
Modeling from data became a powerful alternative. Learning system behavior directly, pragmatically, without needing a full first principles derivation. This raises interesting philosophical questions, doesn't it? Epistemology versus ontology, is knowledge constructed, or does reality have inherent characteristics we discover?
And for control, the goal isn't just prediction.
Exactly. In identification for control, the main goal is to influence and control behavior, accepting practical limits. For non-deterministic systems, models are judged on how well they approximate behavior, considering noise and uncertainty. Perfect matching isn't usually feasible or even necessary. And Occam's razor often applies simpler models, can be more robust and understandable, even if less precise.
What are the core philosophical justifications for using models at all? Why this leap from physical reality to abstract representation?
Philosophically, it rests on induction, reductionism, and mechanism. Induction lets us generalize from specific observations. Reductionism lets us simplify complexity into manageable parts. Mechanism lets us explain phenomena through underlying processes.
And Plato's cave.
A powerful metaphor. It highlights the inherent uncertainty. Models are like shadows abstractions based on limited filtered observations, not reality itself. There's debate, too, between idealism, models as conceptual abstractions shaped by us, and a more moderate approach, balancing model utility with awareness of limitations, especially for complex adaptive systems. The modeling cycle itself involves idealization, which inevitably creates unmodeled dynamics, and then confirmation through validation and refinement.
Which brings us back squarely to uncertainty. There is no certainty, only less uncertainty. The certainty equivalence principle, designing as if the model is perfect, simplifies things but often fails badly in practice. Why? What are the sources of this inescapable uncertainty?
It's the core challenge. Certainty equivalence fails because models are never perfect, sensor noise gets ignored, actuators have limits. Uncertainty itself comes from two main sources. Aleatory uncertainty, inherent randomness, like true noise, and epistemic uncertainty stemming from a lack of knowledge, unknown parameters, unmodeled dynamics.
And emergence.
Emergence is a huge source, especially in complex adaptive systems. Unexpected behaviors arise from interactions that weren't in the component models. Think self-organizing systems, smart grids, traffic flow. Epistemologically, it's not just about identifying sources, but understanding the nature, scope, limits of uncertainty itself. How do we acquire knowledge about it? What is it? How do we reason about it and communicate it?
This raises a fascinating question about methodology. How does Popper's philosophy of falsification, usually associated with science, apply to engineering and feedback control? Model-based control feels inductive, observe, model, confirm. Popper rejected induction.
It's a great question. Popper argued no finite observations can prove a theory true, only falsify it. Observational statements are theory-laden anyway. For him, falsifiability is what makes something scientific. Can it, in principle, be proven wrong by evidence? Corroboration just means it survived tests. Falsification is decisive.
How does that fit engineering?
It aligns perfectly with rigorous iterative testing and validation. We don't just test to confirm, we test to break the system, find potential failures, learn from them. It encourages seeking failure modes for robustness, assessing risks via worst-case scenarios, promoting quality assurance by actively seeking weaknesses.
So when failures happen, falsification provides a framework for responding.
Exactly. If a system fails, we can change requirements, change the design, artifact, or change the underlying engineering theory model. Falsification guides this systematically. challenging assumptions, avoiding quick ad hoc fixes that might hide deeper problems. It can even drive paradigm shifts. It also helps avoid the infinite regress problem seen in some recursive identification methods where initial guesses create dependencies. Requiring falsifiable predictions breaks that chain.
And this idea has been applied in data-driven control.
Yes, Willems formalized it for system identification in '91. The more a model forbids, the better it is. It's incorporated into data-driven control where you evaluate controllers directly against data, eliminating dependence on potentially flawed models. It's more deductive, systematically ruling out bad controllers rather than inductively building perfect models.
This leads us towards postmodernism in control, a philosophy often linked with skepticism, pluralism. How does that apply here? How does it shape design for complex modern systems?
Postmodernism reacted against modernism's certainty, its grand narratives. It emphasizes skepticism of objective truth, focuses on local diverse perspectives, embraces pluralism. It challenges overarching theories like Kalman's attempt at a unified linear systems theory.
What did that mean for control design?
It led to a new vision, the matter-energy-information triad. Information, often as processed data, becomes central. You get the triad of physical systems dynamics data. Data isn't just input, it's integral to design in this postmodern view.
And pluralism.
Directly follows the acceptance of multiple methodologies, viewpoints, no one-size-fits-all. It's about integrating diverse techniques, robust, adaptive, intelligent, data-driven, choosing the best mix for the specific problem. Of course, pluralism brings challenges too, complexity, integration issues.
This sounds like it relates to philosophical debates about realism too. Internal realism versus metaphysical realism. How does that play out?
It's a key tension. Metaphysical realism, MR, believes there's one true, fixed reality, and our descriptions must perfectly match it. Knowledge is uncovering inherent structure. Internal realism, IR, rejects this. It says our understandings always filter through our experiences, concepts, models. There's no single objective truth for control. Different approaches can be equally effective. Knowledge is shaped by our interpretations and their utility.
What does IR imply for control?
It implies embracing pluralism isn't just tolerance. It encourages new representations, theories, designs, different modeling languages, ODEs, discrete time, stochastic, AI, lead to different insights and techniques. The key question shifts from does this controller perfectly copy reality to does the controller behave as expected? Its value lies in its performance, regardless of its philosophical stance on realism. Control engineers, as the book says, must learn to live in a pluralistic world.
Let's shift our gaze towards the future now. Looking back, what were some early predictions about where control systems were headed, say, from the mid-20th century? Did they get it right?
Well, Fuller, back in 1963, anticipated two key directions. First, grounding simple control theory on a more realistic basis, which implies tackling uncertainty, robustness. Second, emphasizing empirical development for complex systems, especially multivariable and adaptive self-adjusting systems.
Pretty prescient.
Remarkably so. By the late 1980s, the community consensus focused on challenges like robust MIMO control, discrete event systems, DEDS, nonlinear methods, geometric asymptotic, and data requirements for distributed systems. Two big themes emerged: rising performance demands reshaping methods and the absolutely transformative role of digital computers becoming integral parts of control systems.
We also have that interesting 1999 Japanese survey on control technology impact. What did it find about actual usage and satisfaction around the turn of the millennium?
It showed a mixed picture. Advanced PID was still huge, about 30% usage, very practical. MPC and fuzzy control were the most used modern intelligent techniques, nearly 40% uptake in factories showing their pragmatic appeal.
And the more advanced modern theory.
Lower usage, around 10% for things like LQG, Kalman filters, H infinity, but increasing rapidly. Compared to a decade earlier, there were big increases in decoupling PID, dead time compensation, Kalman filters, MPC, H infinity, rule-based, fuzzy optimization. Satisfaction was generally up too. High for PID, 60-70% for modern control, except MPC seemed more satisfying, and rising for intelligent control. Yeah. Looking at feasibility versus expected impact was revealing. Advanced PID, widely used, effective. MPC, fuzzy, neural nets, high growth, high expectations. Established modern methods like LQG, H infinity, adaptive. Practical, yes, but surprisingly limited expected future impact, may be seen as mature. Emerging nonlinear methods. Promising, but not yet practical. Optimization, practical and with high expectations.
Bringing us closer to today, those control technology reports from 2011 and 2014 looked at broader societal impact. How has control scaled and spread?
They really chart the expansion from aerospace manufacturing into almost every sector: biomedicine, energy, environment. And the scale has increased dramatically. From single components to multivariable, then plant-wide, now complex systems of systems, SOS, at enterprise or city scale?
Requiring different expertise.
Absolutely. Successful deployment now needs dual expertise, deep control theory, plus deep domain knowledge. Much more interdisciplinary collaboration. Hardware advances in sensors and actuators have enabled this expansion. Quantifying the impact is hard, but economic metrics show huge societal benefits, often hidden.
And key research directions.
Network decision systems, cyber-physical systems, CPS, cognitive control, systems of systems. They share traits. Interdisciplinary, reliant on networks, distributed decentralized, high autonomy, tackling big challenges like smart grids, intelligent transport, integrating with humans.
And the most recent roadmap, the IE's 2030 Control Systems Roadmap from 2023. What societal drivers are pushing the field now?
It highlights key drivers. Smart cities, needing integrated infrastructure, energy, transport, water, using multi-scale modeling, behavioral control for resilience, sharing economy, framing it as a feedback control problem, needing transactive control, multi-level optimization for resource allocation, and critically, resilient cyber-physical systems, CPS.
Protecting infrastructure.
Exactly. Against cyber attacks, extreme weather, requiring real-time reconfiguration, threat detection, safety-preserving control, autonomous recovery, really pushing the boundaries.
This leads us inevitably to ethics. As systems become more autonomous, pervasive, intelligent, what ethical considerations do we face? This wasn't always a big topic in control, was it?
No, historically it wasn't prominent. But Norbert Wiener, the founder of cybernetics, raised serious ethical alarms decades ago.
Prosthetically, almost.
What did he foresee? In cybernetics, back in '48, he predicted a second industrial revolution via automation and AI making human skills worthless. He called for a society based on human values other than buying or selling to counter this. He felt deeply uncomfortable, morally, about contributing to a science with potential for great possibilities for good and for evil.
He was pessimistic.
Deeply pessimistic that power derived from these systems would be used well. He feared it concentrating in unscrupulous hands, leading to a world of Belsen and Hiroshima. He suggested focusing science away from military exploitative uses towards physiology, psychology, educating the public, though he admitted having very slight hope back then.
A profound early warning.
It's an enduring ethical challenge we're only now really starting to grapple with more systematically. Today, ethical design principles for autonomous intelligence systems based on anthropological, political, technical pillars are being developed and are absolutely crucial for control systems engineering.
We've covered an incredible amount of ground today, from ancient water clocks and automatic doors showing that drive for self-regulation, through the mathematical rigor of Maxwell and Lyapunov, the practical brilliance of Black and Bode. We saw WWII catalyze modern control, leading to Kalman's elegant state space, only to reveal its Achilles heel, facing real-world uncertainty.
Pushing the field into postmodern paradigms, robust, adaptive, intelligent control, embracing complexity and pluralism.
Exactly. We looked at future roadmaps for smart cities, resilient systems, and reflected on Wiener's unsettlingly prescient ethical warnings. It's so clear this field is far more than just algorithms. It's this dynamic interplay of history, philosophy, engineering practice, and our very understanding of knowledge and reality.
It really is. And if we connect this all back to the bigger picture, you see this historical swing, right, between grand unifying theories like Kalman's and the sheer pragmatism of using multiple, overlapping, context-dependent approaches. What does this ongoing pluralism we see today truly imply for how we think about truth in engineering?
That's the core question, isn't it?
Does an effective control system need to perfectly copy reality as it is in itself, chasing that ontological correspondence science often seeks? Or is its ultimate value simply determined by whether it behaves in the way it is expected to, regardless of its underlying philosophical stance on realism? That fundamental question, internal versus metaphysical realism, continues to shape how we design and deploy the invisible threads of control in our world. And it's a question that surely impacts your own work and the work of everyone listening.